All right, so yeah, so you want to take the left-hand side of the equation and the right-hand side of the equation and compare the charges for them. So, all right, so let's take a look at that then. If we look at the right-hand side of this equation, we have, I'm summing up the total charges on all the different molecules or compounds on the right-hand side of the equation. So I have 6 plus from the hydrogen, and then I have 0 from the alumina over here. So the total charge on the right-hand side of the equation is plus 6. If we look at the left-hand side of the equation, the total charge is, I have 0 on the aluminum, and then I have 0 on the water. And so my total charge over here is 0. And so the charges have to be balanced on both sides. You can't create charge from nothing. And so to fix that, what we can do is we add in 6 electrons. So 6 electrons takes care of this because an electron has a negative charge. So the negative and the positive cancels out. And so now it goes from plus 6 to 0. And so now my charges match on both sides. And I can come down here and deal with this one in the same way. Say, okay, what's my total charge on this side of the equation? It's 0. What's my total charge on this side of the equation? It's plus 4. And so I want to balance this out, so I add 4 electrons to the left-hand side of the equation. And now everything is balanced out. Okay, so we're getting there. Step 5 is going to be to, now I guess is you're truly balancing out the electrons. Balance the number of electrons So we're going to do this. When I say balance the number of electrons, I'm talking about the number of electrons lost in the oxidation and the number of electrons gained in the reduction. So we're talking about between the two half reactions. So you can see up in the top part of the reaction during the oxidation, I'm losing 6 electrons. That's what we've kind of written out here. We're saying, okay, we got water, we added to aluminum, we form this aluminum oxide, and we lose 6 electrons. And I lost something. Hold on a second. Oh, I put that on the wrong side. Yeah, so over here we see that we lost 6 electrons. And down here what we're saying is it's like I have manganese oxide and I'm reducing it, so I'm adding 4 electrons in. So we're sort of treating the electrons almost like they're reactants. And I'm saying I'm adding 4 electrons to the manganese oxide to get manganese 0. That's the reduction reaction. And up here I'm stealing 6 electrons from the aluminum. So these things have to balance out. The number of electrons lost in the oxidation has to equal the number of electrons gained in the reduction. And so we want to go ahead and multiply both of these by some coefficient that makes the number of electrons equal. And so we can do that here. Let's see. So we've got 4 electrons at one, 6 electrons on the other. So if I multiply this top one by 2 and I multiply the bottom one by 3, so multiplying the whole equation or the whole chemical equation by some coefficient. The only goal here is that we want whatever this number is times this number has to be equal to this number times this number. So I need my electrons to balance out. So 2 times 6 gives me 12. So that takes care of the, the electrons up here, and 3 times 4 gives me 12, and that takes care of them down here. So we need those electrons to be equal. So you're just looking for a number that does that. You could, if you don't want to think about it at all, you can obviously multiply the top one by 4 and the bottom one by 6. That'll also get you there. This just helps keep the numbers a little more manageable. But ultimately, all you're trying to do is get those numbers equal. In the end, no matter what numbers you use out front here, as long as these electrons end up equal in the final result, it'll all kind of work out, because we're going to go through and we're going to divide everything by the lowest common denominator to kind of fix the coefficients in the end. So, all right, so now we rewrite them again. So you can see these things take a while. We rewrite them again. So now I'm going to go ahead. Let's see, where can I write? I'll just write underneath each one. Doesn't want to do it for me. Oh, I see what the problem is. Oh, screw it. All right, here we go. So I'll rewrite it right underneath it. So we end up with 6H2O. I'm just distributing the 2 throughout. So 2 times 3 is 6, 2 times 2 is 4, and you just want to do that across the entire reaction. So now I see I have the 12 electrons, which is what I wanted. And then I can do the same thing down here. So I end up with 12 electrons on the left-hand side. And then I want to make sure that I continue multiplying this through. So 3 times 4, 3 times 1, etc. So I end up with 12H plus 3 manganese oxides, 3 manganese, and 6 water. Okay. Now we really are close to being done. So now everything really is balanced. So all the hydrogens and oxygens are balanced. We balanced our charge using electrons, and then we made sure that these two half reactions match one another in terms of electrons lost and electrons gained. So now we're ready to add these two back together. So I'm going to take my I'll take my oxidation reaction. And I will take my reduction reaction. And I'm just going to add them back up. This could be like step 6. So there's several different ways you can solve these. So if you learned a different way in high school or something that you're really comfortable with, that's fine. But they all follow like a very similar workflow. All right, so now we're going to add these back together. So the things that are on opposite sides of the chemical equation will cancel each other out. I'm trying to think of what the easiest way is to show that. I'll just write it all out and then I'll show it that way. All right, so I'm going to just take everything on this side and just write it out in the reactant side, and take everything on this side and write it out on the product side, and then we'll look at how things cancel. You can cancel at this stage if you want to, it doesn't really matter. So we end up with 6H2O plus fluoralumina. That's coming from here. And then we end up with 12 electrons plus H plus 3 manganese oxides. So that's all just down here. And now I'm going to do the same thing over here. I'm going to take this and then I'm going to add it to that. So we've got 2 aluminum oxides plus 12H plus 12 electrons plus 3 manganese plus 6 waters. So at this point, you're pretty close to being done. You just need to make sure this is a pretty wonky looking equation, but a lot of this stuff ends up canceling out. So just like in, if you're looking at like algebra, if you're doing something in algebra 2 or whatever, and you're subtracting out things from different sides of the equal signs, they cancel exactly the same way. This one works out a little bit too perfectly. The electron should always cancel out. So you notice there's 12 electrons on the left and 12 electrons on the right. But the water and the hydrogens don't always cancel out. Oh, I accidentally canceled the wrong thing there. I'll show you another one where things don't cancel quite as cleanly. But so the 12 electrons cancel out there. We see that the protons actually cancel out. Water cancels out perfectly, as in like 6 and 6. And then what we end up with in the end then is just 4 alumina plus 3 manganese oxide goes to 2 aluminum, 2 aluminum oxide plus 3 manganese. And so that's our final equation. So this thing is balanced. And if you want to check that it's balanced, of course, you can go through and check that all the elements make sense. So we have 2 aluminum here, so 4 total. We have 4 over here. We have 3 manganese, 3 manganese. We have 6 oxygens, and we end up with 6 oxygens. And you can also check that the charge is balanced. So on this side of the equation, we have 0 charge. And on this side of the equation, we have 0 charge. And so that is more or less how you balance a redox equation. I'll show you one more. I hate these things are so long. But I want to show you one more example where things don't cancel out quite as cleanly. Let's look at a riff on, let's look at this slight change on that. So we'll use, if we look at manganese, so we're going to use manganese again, but instead of using manganese O2 or whatever, we'll use manganese oxide, or manganate, I guess, ion. We'll add that to iron 2. We'll see that the iron gets oxidized to iron 3. And the manganese gets reduced to +2. So our first step, this one's a little bit more complicated than the last one, but our first step is to just figure out what's being reduced and oxidized. So it's very obvious that the iron is being oxidized. It's just going from +2 to +3. There's nothing really to calculate there. So our oxidation is just this. So we're breaking it up into the half reactions. I'm going to work this a little bit faster than the last one. This has a total of -1 charge on it. And so to figure out what the charge on the manganese, we say, okay, well, the oxygen must have -2. And so this total charge on the anionic half of this thing is -8. So I'm saying what -8 gives me -1. And that tells me that the manganese must be +7. So manganese is being reduced from +7 to manganese +2. All right, so now we just go through the same process again. We take the 2 half reactions and we balance out anything that's not oxygen or hydrogen. And you see that for both of these, it doesn't matter. There's nothing to balance. Manganese, we've got 1 on this side, and we've got 1 on this side, and iron, we have 1 on both sides. Yeah, in this one, I'll talk about the acid-base thing when I get to the end of it. Wait until I get to the end of this problem. I'll explain the acid-base thing in terms of how we balance. But okay, so we're starting out. So the question that came up in the chat window was, how do we know for an acid base and like what's the difference? So in the top reaction, it doesn't really matter if you're an acid or base, just because of the way it ends up balancing out. But in this equation, it will, and I'll show you kind of what the difference is. So regardless, the number of steps that you follow is the same. It's just if it's in base, there's 1 extra step, and we'll get to that. So we have these 2 half reactions, so we're going to go through and we're going to balance them out. And so the iron one's going to be pretty straightforward to balance. The manganese one's going to be a little bit more of a pain. Okay, so let's look at the oxidation half first. What do we have here? We have iron +2 going to iron +3. So we balance out the oxygens. There are no oxygens on either side, and there are no hydrogens, so I don't have to worry about adding water or adding H+ or anything. The only thing I have to worry about balancing for this half reaction is making sure that the charge is balanced. So you notice that the net charge on the product side here is +3, while the net charge on the reactant side is +2. So how do we fix that? We're going to add an electron to the right-hand side. And so this is what we expect for an oxidation. So in an oxidation, the electrons are going to end up being on the product side of things. You carry down the negative charge. Yes, that's just me being sloppy. Thank you. So remember, this negative charge applies to the entire manganese oxide here. Sometimes it can be hard to see because I'm annotating that the manganese here has a +7 on it, but the minus here is applied to this whole thing on the outside. But yeah, so you've got iron +2, it goes to iron 3, and we've lost an electron. So we're treating the electron like a reactant or a product, even though that's not really how we typically think about them. And that's it. So this oxidation half reaction is completely balanced now. So now we want to come down and balance this other one that's a little bit more of a pain. And so we're going to balance out our oxygens. So we have 4 oxygens. So I add 4 water in. So now the oxygens are balanced. Of course, that screws up the hydrogen count. So now I need to go back to the other side of the equation and add in H+. So now we're almost there in terms of balancing. We just need to balance out the charge in this bottom one. So our total charge on the left-hand side of the equation is +8. And then we're taking this charge. We don't care about the individual atoms' charges. The net charge is just the charge on the manganese oxide. So -1. And so the total charge on that side is +7. So we get -1 from the one manganese oxide that we have, or manganate or whatever this thing is. And then we have a +1 here, we have 8 of them. So we get +8 from the protons. And so when we add that all together, we get +7 for the left-hand side of the reaction. We come over here to the right-hand side, we've got water, which is neutral, so we don't have to worry about it. And then we've got +2 for the manganese. So clearly +7 does not equal +2, so we need to fix that. And we fix that, remember, with electrons. So we have +7 over here, so we just want to add 5 electrons. So now I've added 5 negative charges. So, negative, oops. So if we take -5 and we add it to +7, we end up with +2. And now our 2 charges are equal to one another. So now we've balanced the reduction part of this reaction as well by balancing out the charges there. Okay, so now we're at the point where we can add these things together. So let's do that again. So this one's a little bit more interesting. Oh, wait, sorry, one more step. This one's easier in this regard. So we need to make sure that the number of electrons that are lost in the oxidation is equal to the number of electrons that we picked up in the reduction. And so we see here we've lost 1 electron. That doesn't make sense because clearly we've picked up 5 electrons in the reduction. So the way that it's written now would imply that we just kind of invented 4 electrons. So we need to fix that. So all we have to do that is multiply this top equation by 5. And so I will, let me move this down a little bit. All right, so I'll rewrite that right here. So I've got 5 iron 2s And then the 5 applies to everything. So 5 iron 3s. And then I get my 5 electrons, which is really what I'm trying to do here. And now I want to go ahead and balance these things out. Or add these things together. Not balance them out, add them together and see what cancels. So again, at this point, you can kind of cancel across. So I can say, well, 5 electrons appears over here and 5 electrons appears over there. But let me go ahead and write it out a different way. This one will be a little bit more illustrative, I think, of what's typical for these types of problems. So we have 5 electrons. I'm taking it from the bottom this time, plus 8H plus. Plus manganate. Plus 5 iron 2. And this goes to manganese plus 2, plus 4 water, plus 5 iron 3, plus 5 electrons. Okay. So the electrons should cancel out. That should always be true. So you'll see there's 5 electrons on both sides of the equations. And so those just cancel out cleanly. You'll notice though in this one, we don't get to add and subtract any water. But you'll notice in this one, the H plus and the water don't cancel out at least. And so in our final equation, we just end up holding on to those. And so this ends up being our final equation. Yeah, this ends up being our final equation. So you'll note that in this one difference is that we end up with some protons over here. So if we're balancing an acid, so regardless of whether, so in a reaction, it could say that it takes place, so a piece of information would say like, oh, it takes place in acid or base, or it could take place in something neutral probably. But regardless, for example, this one up here, it doesn't really matter if it's acid or base. It could take place probably in something that's neutral. But takes place in acid or base, it doesn't matter, or neutral for that matter. It doesn't matter what it is. You follow this exact set of guidelines. So you add H plus and do this thing. The only difference is, so if we're in acid, this is our balanced equation in acid. You're done. But if we to balance it in base, there's one more step. So in base, we know that we're not going to have any H plus around, so it doesn't make sense that the equation would look like this. To fix that, we just want to add in enough OH minus to get rid of it. So what we'll do is you add an equal number of OH minuses to whatever the H plus is to both sides of the equation. So I'm going to add 8 OH minuses to the left-hand side of the equation. And I'm going to add 8 OH minuses to the right hand of the equation. So you can see, or hopefully you can kind of see that like a lot of the way that this works, like all the balancing and stuff, it is the same as kind of how you do it in algebra 2, right? Like, so I'm taking 8 OH minus and I'm adding it to one side. It kind of feels like I'm pulling them out of thin air, but it doesn't matter because I'm adding it to the right side of the equation as well. And so it's kind of effectively like multiplying everything times 1. I haven't really done anything. As long as you do the same thing to both sides, I haven't changed anything. It's not exactly the same, but you can also see that here I have 5 electrons on the left and right, and so they cancel each other out. Anyway, so the only tricky thing about this is I have H plus and I'm adding OH minus, and so I combine these two to form water. And then I rewrite my equation. So now you see that there's no H plus in there. I've gotten rid of that and turned it into water. And now this is useful because this allows us to show that. So we've got 4 water on the right-hand side and we've got 8 water on the left-hand side. And so we shouldn't have products and reactants appearing on both sides of the equation like that. That is not what we want. So what we do is we do what you would do. I'm going to write it out like sort of very, I can't think of the word. I'm just going to go like over the top with how I'm illustrating it here. So normally I would just do this in my head, but really what we're doing is we're subtracting. If you kind of think of this like an equal sign, it's like I'm subtracting 4 waters from over here and I'm subtracting them from over here so that I can move everything to one side of the equation. And don't take what I'm saying about like working just like algebra too literally. Obviously, some of this stuff is not, this is an actual like physical process that we're kind of grounded to here. So it's not like we're just doing some math operation where we've made up the rules, which is kind of what algebra is, or all math, you know. You make up the rules in math, you say what the axioms are. In physical sciences, we're kind of stuck with what nature gave us. Anyway, and then finally now we're at the final equation. So this is what it's balanced in base. So in acid, we do everything, you know, we balance out everything with H plus. In base, we know that there's not going to be any H plus in the final reaction because we're in base, right? We know that the concentration of H plus in a basic solution is virtually nothing. And so we have to go through this extra step where we add in OH minus. And so we combine that with the H plus and that gives us water. And so this is nice because it gives us this extra step, which sometimes happens even up here. We have water appearing on both sides of the chemical equation, and we don't want that. So we take the water on that's the smaller number, and we subtract it out to get 0. So this just totally cancels out. And then over here, we have the remaining 4 waters. And then we have our final equation. And we see that in this equation, we have some base that appears on the right-hand side. Did I unbalance the charges? The charges should not be unbalanced. So if I did, I screwed something up. Let's take a look. So when you're checking, so that's a good question. So at the end of these equations, there's a lot of steps here. You know, like if we go back through, there's just a lot of crap happening here. And it's very easy to make a mistake. And so it's always smart to kind of go through and check your charges. Hopefully, yeah, I may have messed up the charges. Let's take a look. So the things that you check first are make sure that you can make sure that the atoms balance out. So I have 8 hydrogens here. I have 8 hydrogens there. I have 8 oxygens here. I have 8 oxygens on this side, 1 manganese, 5 irons, 5 irons. So that all balances out. What about our charges though? So I get, I'll do it explicit. That's the word I was looking for. So I'll do it really explicitly here. So I have 4 times 0 for the water, plus 1 times -1 for the manganate, plus 5 times +2 for iron. So that comes out to be what? 10 minus 1 is 9. Yeah, and 0. This is silly to write out. 10 minus 1 is +9. And then over here we have plus 2. So I got 1 times plus 2 plus 5 times plus 3 plus 8 times minus 1. And so that ends up being plus 2. Let's see, 15 and 2 is 17 minus 8. And so, yeah, so that equals plus 9 as well. So our charges are good. No, it's a good question. And it's yeah, the oxygens. All right. Yeah. So several good questions here. And I think even though you guys are realizing that um, that you're calculating, you're kind of calculating this wrong and saying, oh, the charges have changed, or that I have too many oxygens on one side or whatever. Those are really easy things to do because, like, look at how the monstrous kind of way that we have to deal with this thing. So we're balancing one equation, and this one could get uglier if we didn't have iron, we had something else, and it just has so many different steps in it. And then when we finally get to the end, it's just this mess of crap. So you just have to be really careful and practice. Yeah, one mistake messes it all up. It's just like in I don't know, like in like calculus or algebra or something. It's like you forget a negative sign somewhere and you get this complete mess of things. But the nice thing about this is at the end, I don't know if it's nice, but at the end, because you can kind of check to see if you screwed up. So if your answer is correct. So in this last step, you just check to make sure that the atoms balance and the charge balance. And if it didn't, it kind of hints that you made a mistake somewhere along the way. You don't want to make too many mistakes and have to go back and fix them because you have a time limit on the exam, but that is kind of a nice piece to have at the end, which you don't have usually in like a math class. So just be careful, I guess, is my main thing. This type of stuff, balancing reactions, once I'll make this as a caveat. So if you're not good at oxidation states, this is a complete nightmare. Like doing these types of things is a complete nightmare. So that's your starting point. Don't even attempt to balance redox equations if you're getting kind of caught up on like how I'm getting manganese is plus 7 here. That you're just you're never going to be able to do it. But once you know the oxidation states, the rest of it is really just about having really good bookkeeping. So at each step, you just want to make sure that you're really careful and you have a very good bookkeeping method to make sure you're not losing charges. You're not losing, like, remember, I lost the negative charge up here when I rewrote. Where did I rewrite it at? I don't know. Somewhere along here, I lost I'm still missing a negative charge right here. Right. So if I'd have dropped that negative charge and somebody wouldn't have pointed out and I wouldn't have realized, right, I'd have gone through this whole thing. Forgetting about that negative charge would have screwed me up when I balanced my charges out. And then in the end, I'd have been kind of scratching my head saying, damn it, where did I go wrong? And at that point, you kind of have to start over. So just try to keep really, really good track of everything and have really good bookkeeping and just kind of practice these. So if you rush through them and miss something, it can kind of really cost you a good amount of time. So redox reactions are I don't want to say this the starting point, but they kind of are the starting point for understanding electrochemical cells. Which is what we're going to look at next. So batteries are a big deal, obviously, right? Like that's the energy in general for us as modern humans is everything. We're allowed to kind of live like this and have computers and all this kind of cool stuff because of fossil fuels for the most part, but also our ability to kind of store energy. So how does the battery inside of your computer work, et cetera? Those batteries are all based on stuff that's redox reactions, essentially. A lithium ion battery is a redox reaction. What would the reaction look like on a molecular level? I mean, this is pretty detailed. I guess you could draw out like what the physical, like kind of what the crystal structure of these things look like, but this is more or less what this thing would look like at the molecular level. What about when it says my battery needs to be replaced? Yeah, so we're writing these reactions out. So these reactions are reversible. So we're writing them out in one direction, but so in this direction, this is a good segue into the next thing. Let's start talking about batteries. So why does your battery go bad and need to be replaced? It's because the reaction in the battery is reversible, so I can recharge a battery. So for example, if like I'm getting, let's say I'm running this reaction, and I'm getting some free energy off of it, you know, so I'm getting energy from, what is this, oxidizing iron or whatever. So I'm releasing energy, and that's allowing me to kind of run my computer. I can then plug my computer into an electrical outlet and drive the reaction in the opposite direction, and sort of reduce the iron back down. We're going to talk about this in more detail, and then allow that reaction to go again. So I'm storing energy through these redox reactions. So in this reaction, for example, if we're looking at it just in the context of iron, you can think that, okay, as iron goes to iron 3, it releases energy, and then when I want to recharge, so I can harness that energy, let's say, to run a monitor or run a phone or something, but then eventually I run out of iron 2, like it all goes to iron 3. So then what I do is I plug it in and I use the current from my outlet or whatever to drive that reaction back and reduce the iron back down to iron 2. So I add electrons back in. Now I've got it back down to iron 2, and I can repeat that process over and over again. So it's reversible, but it's not, the reactions typically aren't perfectly reversible. So something will go bad in it. So we'll talk about what anodes and cathodes and stuff are, but like there's physical materials in there, and you end up with side reactions. So the number of cycles that you can go through on that is limited. So that's kind of what it is. So when people talk about battery breakthroughs and stuff, there's a whole bunch of other things you have to consider aside from just like how much energy you can store in it. You have to be able to do that over and over again. I'm trying to think of a good example of that. It's the same as like if you think in terms of something that's mechanical, like a spring, right? I can take a spring and kind of press it. You know, I can compress it down over and over again. I don't know. I don't know. I draw it coiled even more tightly. Let's see. So yeah, if I take this spring and press it down, I can then like, this is a reversible process. I can go back and forth between kind of compressing this, but eventually that spring is just going to break, right? So there's a cycle, there's sort of a number of cycles that it can go through before the material just kind of like gives out and breaks. And that's why your battery needs to be replaced every now and again. So even in a reversible process, like in a spring or something where you kind of, you know, restoring the potential energy in the spring is in this compression here, eventually the spring gives out. And that's the same thing is true of your battery. These reactions, and we haven't looked at this, are really reversible if we put energy into them. But eventually something in it gives out, like the polymer matrix in the lithium ion battery or something will go bad. But yeah, okay. So the next thing we'll talk about, so the LEs in this are really, really good for the electrochemistry chapter, at least in my opinion, are really good for the electrochemistry chapter. They're built to where it doesn't really completely require electric component. So make sure to keep up with those and watch those videos. Try not to rush through those and get a completion grade, just for the completion grade. But we're going to start talking about electrochemical cells. So we'll talk about galvanic cells and kind of how to set up a battery. The batteries that we're going to look at are going to look kind of weird, right? We're going to like look at them in terms of having like flasks and salt bridges and all this kind of crap in them. And that obviously is not what a battery in a laptop looks like, but it is kind of the simplest way to kind of build a battery. And they do work off of identical, work off of identical things. So we're going to build a battery that looks, you know, something like this, where we have two beakers, and we have an anode and a cathode, and like, you know, a wire that connects them and all this kind of stuff. This is a very rough ass drawing I'm doing here. We have what's called a salt bridge and all this different type of stuff. And so we're going to dissect this. In detail and talk about how we can build this. So there's a ton of stuff that we can look at here, but we'll look at standard reduction potentials, and you can actually understand how to set up an anode and cathode, exactly how much energy you can get off of this and how much work can be done, and why these things are reversible. And that, you'll see. So we get to that on Friday, and then we have Monday of next week. And then we have Thanksgiving, and then we have another Monday after that before the exam. So yeah, so we'll spend the rest of the time on electrochemical cells. But yeah, so the starting point for all of this though is these reactions. I wish I had a little bit more time to kind of talk about that, like what's happening at the anode and what's happening at the cathode. There's chemical reactions that are happening there. Anyway, all right. So where you should be, definitely. I mean, I don't know where our exam is. Not next week, but the week after that. But next week is Thanksgiving, so make sure that. Yeah, I guess I should go in and put dates on them. I can make them do this Sunday. I don't really care that much. I mostly just to keep you guys on task. Whether they're due, before the exam. But yeah, so we have Thanksgiving next week, so make sure to build that in. I doubt we'll do the drop test for the final exam. I need to talk to the other instructor about that. I want to see how the grades on Unit 4 shake out, because grades on Unit 3 were pretty good. I know you guys don't want to take the final. I don't know. Let's get through this bulk of the material, and then we can figure it out, what the final is. Usually usually we kind of rush through. Usually I'm a little more on top of that just because people sometimes have to travel and stuff, even though it aggravates me that people will schedule travel in the middle of finals week. I still try to be accommodating, but since we're all kind of stuck in home, it's a little less crucial that we figure that out now. But for right now, just assume that everything's going to be the same way, the syllabus. That's sort of the worst case scenario. Um, but yeah, right now I would definitely, I really feel like you should be at the point where you can balance redox equations. So don't drag your feet on that. And if you're one of the people that are struggling with assigning oxidation numbers, then you're like pretty behind. Not fatally so, but you definitely need to get that down now. So work on your oxidation number stuff, and work on balancing these redox equations, because we're gonna kind of take that for granted as we go through all these electrochemical cell type things. All right, let me take a break, and I'll see you guys in office hours in like 5 minutes. All right. You guys have specific questions?
Could you please go over number 20 from the exam?
Exam. Did we go for 20 last time? Let me take a look.
Yeah, I didn't make it to the last one and the recording's not up, so I'm not sure.
Oh, right. Oh, yeah. Yeah, let me look at it real quick.
Okay, thanks.
Yeah, I need to put my recordings up. I'm bad about that. Exam 3. This is the one where it's potassium hydroxide being added to calcium nitrate. Is that right?
Yeah.
Okay. Yeah, I think we went over this. We can go over it real quick again.
Thanks.
Oh, yeah. Yeah, I think that's the last one we went over. So this one is, we have 0.015 moles of KOH. Oops. And then we have 1 liter of 0.0010 molar calcium nitrate. And then we know that the KSP is equal to 6.5 times 10 to the minus 6th for calcium hydroxide. And so what we're trying to figure out here is, so you're taking, so let's see, you've got a liter of which is essentially the nitrate doesn't really matter. It's really 0.001 molar calcium plus 2. And then we're adding in, potassium hydroxide pellets or something. And so we know the KSP over here, and we assume we're at room temperature or whatever. And so we know that whatever the concentration is of calcium times the concentration of hydroxide squared has to be, the way to think about it is it has to be the amount that's in solution will equal 6.5 times 10 to the minus 6. If you're below that number, then you're fine. The KSP sort of sets the max that you can have of calcium and hydroxide in solution. I'm not sure I'm saying that in a way that makes sense. So we have 0.001 molar calcium dissolved in here. There's no hydroxide at all. So we don't even really have to worry about the solubility. But now we're adding in 0.015 mole of hydroxide. And so whatever the final concentration comes out to be of hydroxide, we can take that and compare it to the KSP. Let's just go ahead and do that, and then I'll have some numbers to talk about. So we're in 1 liter, so this is squared. Phone calculator. So we end up with 2.25 times 10 to the minus 4th for that, and then this just remains 1 times 10 to the minus 3. And we can multiply those two numbers together. we come up with 2.25 times 10 to the minus 7. But yeah, since 2.25 times 10 to the minus 7th is less than 6.5 times 10 to the minus 6th, we're not going to see any calcium hydroxide form. That's the way to read this. So it's sort of like you're before you get to the saturation point or whatever. I think one way to look at it is you can, can you call this Q? I was thinking about this last time. I think maybe you can. But the main thing is just that if when you write out this expression, because I guess it's not K, so you have to call it something. Whenever you write out this expression, if it's less than the KSP, which it is here, then you don't see any precipitate. So, these things stay in solution as calcium plus 2 in hydroxide. So it's like you have calcium in solution, that a certain amount of, if we think about this, we know that a certain amount of calcium hydroxide can go into solution. And so what that exact amount is determined by the KSP. And so the typical way we're kind of looking at these things is like, we'll say like, oh, we add a chunk of calcium hydroxide to the bottom, and then we're just seeing how much calcium plus 2 and OH minus comes off of it. Here we're kind of doing the opposite. We're saying, okay, we have calcium, and then we're going to kind of titrate in some hydroxide into it. We're just going to add a little bit in. Are we going to form a solid at the bottom? And if this number here is less than the KSP for these concentrations, the answer is no solid's going to form. If it's greater than the KSP, then yeah, you're going to form some amount of solid there. That's how that works. And so I think let's see, the solution is, the solution is unsaturated in no precipitate form. So you're before the saturation point. That's the answer.
Okay, thank you. That makes sense. Yeah.
Good. Yeah.
That makes a lot of sense.
Yeah, so places, not that you're worried about the practical applications, but places where that comes up is like certainly in oil and gas, but anywhere where you're dealing with like pipes and boilers and that kind of stuff, you're always going to have some concentration of metals in the water, because that's just how water is. It's just always got something dissolved in it. And so this is a way that you can kind of calculate if you're going to have problems with scale, which is what a lot of companies deal with. So you get scale buildup on the pipes. If I don't know what you guys are all going into, because this is the first course, so it could be engineers or medical students or probably something else entirely. In medicine, I'm not entirely sure where you would worry about it as much. All right.
How far along are you on rectifying exam number 1?
I've got it mostly worked out in the spreadsheet. I just need to go in and like put in one more formula and have it fixed. Do you not know your score?
Yeah, I know my original score. I'm just getting close to the end of the semester, and I just wanted to make sure you didn't forget. But if
No. It's one of those things that I need to get to. That just like, I don't know what it'll get fixed, especially before we go into the final, because obviously we're going to drop one of your exams. So yeah, the other thing that needs to be fixed in Canvas is like the way that they're inputted is in terms of points and not in terms of percentages, the way it ends up calculating your grade. So the final grade that it calculates in Canvas is messed up as well. So there's a couple of things that need to be fixed. It's just the Canvas interface is a pain in the ass to deal with, so I've been putting it off. But yeah, I was hoping to have it done before the last exam, and it just didn't happen. Let's see, question 15. What's question 15? What's the text for it?
It's the one that starts with the isotope of radon. Radon.
Radon, yeah. I guess radon. I don't know if we actually worked this one out. Okay, so in this one we've got radon 222, and we know that T1 half is equal to 3.8 days. And then the question is, how long? Let me stick to print here. How long for 75% of a sample to decay? Answer, they want the answer in days to 1 decimal point. Yeah, so let's see, we need our first order equations here. So we know that, so first of all, it's a radioactive decay process, so we know it's first order. And so we're going to be using our first order equations for this. One second here. So you're going to start out by calculating your workflow as you calculate K from the half-life, and then you can take the rate constant that you calculate and plug it into the the integrated rate law to figure out how to relate concentration and time. So we know that the half-life so we know that the half-life is equal to 0.693. 0.693 divided by K. And we know that the integrated rate law for this is the natural log of whatever the substance is, in this case radon, equal to negative KT plus natural log of whatever our initial concentration was. So we know that our half-life is 3.8 days. Yeah, okay. All right. Sorry, distracted. So we have a half-life of 3.8 days, and we're trying to figure out how long for 75% of the sample to decay. So since we know that, since it's a radioactive decay process, we know it's going to be first order. So that tells us what equations we're going to be using. Anytime they're asking for like concentration, like how long something's going to take for a particular concentration to, either like appear or disappear or whatever. In that case, you're going to be using the integrated rate law because that's what it does. It relates concentration at some particular time to whatever, the initial concentration. So you can think of it as like, I have the initial concentration over here. If I want to figure out how much of the product is going to be there or whatever after a certain amount of time, then I add in this quantity negative KT. So I take my initial quantity, I take the natural log, but I add in this little piece here, negative KT, and it tells me, it kind of spits out what the concentration will be at a particular time. But in order to do that, what I need is K, and I can calculate that from this. So we can just say that K is equal to 0.693 divided by the half-life, which is 3.8 days. And so we can express this as 0.18 inverse days. And then we want to come over here and we want to just kind of use that to figure out what our time is. So yeah, so we're looking for T here. So we'll go ahead and solve for that. Immediately, we'll say natural log of A sub T minus natural log of A sub O divided by K is equal to T. I guess we have a negative sign that we have to deal with there. And then we just go ahead and plug it in. So since it's saying 75%, we can just choose our own numbers. We're going to say A sub O is equal to 100. And we're going to say A sub T. We're saying how long for 75% of the sample decay. So that means that A sub T is going to be equal to 25, because that's what we'll have left over after the decay process. So I think that's really the only tricky thing, maybe. So it's saying how long for 75% to decay. So we're saying, okay, well, what's the concentration going to be after 75% is decayed? It's going to be 25%. And then we just plug in some values here and we should get an answer. So it's natural log of 25 minus natural log of 100 divided by negative 0.18 inverse days. And that'll give us our time. And I come out with 7.7 days. Oops. And we can kind of check to see if that's reasonable. So if the half-life is 3.8 days, yeah, I mean, there's probably a way to do this analytically, actually, since it's such an easy number to deal with. But if the half-life is 3.8 days, then we know that the first half will take 50 and the second half will take, so I'm sorry. So if we start out with 100, then we know after 3.8 days, we'll have 50. And then, yeah, after another 3.8 days, we'll have 25. So that's the easier way to do it. I come out with 7.6 if I do it that way. But yeah, so either way works. They both take you to 7.7 or very close to 7.7 days. Let's see what the actual answer was. Oh, they let you go plus or minus 0.1, so it doesn't matter. Okay, got it. Cool. Yeah, putting in I think that's the mistake. It's just putting in 75. Just be careful of that. And realizing that A sub T is referring to the concentration of this, not the concentration of what it's decaying to. Other questions?
Dr. Dragna,
Yep.
for exam question 1, what was like the answers? Because these were one of the questions where like you have to select all that apply.
Yeah, and then also that the KSP is equal to the Q with the sodium. It's these two. So this falls out of the stoichiometry, and then this naturally just falls out of the definition of KSP.
Okay, because I know one of my friends, when she was asking me about that question 1, we put one of the same answers, and then she said she got it wrong, but I got partial credit. And then she was emailing me about it, and so we were confused.
Oh, I don't know. She put 1 but didn't get the other one and got partial credit for it, and you did not, or something?
Yeah, and I don't know what happened, but like And she said she was reaching out about it, but never got a reply.
Oh, yeah. I don't know. I guess I can look into it. I can look at my email or something. But probably, I mean, whatever it is, it's going to be whatever it's going to look like on my end, no matter what ended up actually happening. Like she did not put in whatever answer. Like I guess Canvas could have glitched, but probably the answer that she selected is not the answer that she thinks she selected or something, is my guess. Or not, or she selected it by mistake or whatever. Like, does that make sense? Like, even if,
Yeah, I just wanted to know, like, make sure what like the correct answer was because I wasn't.
yeah, it's those two.
Thank you.
I guess what I'm trying to say, I don't sound like a jerk saying it that way. What I'm trying to say is usually it's very unusual for the multiple choices to be wrong for one person and right for another. Usually it got inputted wrong, or it's harder to say what happens on Canvas. That's usually with Scantron, but something went wrong in terms of what we'll see. So.
Okay, thank you.
Question 13, the correct answers were NO3 minus and K plus, right? Those are the correct answers.
Let's see. 13. What's the text for 13? Sorry, they're not numbered on here, so.
Identify the spectator ions in reaction between.
Yeah, potassium and nitrate.
Okay, not K2 plus.
Let me look at the answer choices here. Yeah, not K2 plus. Yeah.
All right, I understand. You don't have to write it out. I just wanted to check. See about my
Yeah, K2 is not a poly. I guess you'd have be like a polyatomic cation or something.
For the multiple question or multiple answer questions, it was pretty much all or nothing, correct?
I don't know. I'm like
Because
looking at it on my. I get confused with how to look at it in the Canvas thing. Let me look at the details.
Because for the first one, or for the first question, I got one of them right and the other one I didn't, and it just counted it all wrong. So I wasn't sure if it was all or nothing.
I honestly am not sure. Just looking at it on my end, I have to go and look through the answers. Let's see. Yeah, I'd assume it's all or nothing because I guess it could like subtract points as you miss the other ones. I'm not sure that Canvas allows you to program in that much fine tuning. Let's see. Question breakdown. There we go. That should tell me. Oh my God, I hate this software. Although it's better than some other stuff. I had to use Blackboard when I was in college. That was really crappy. Let's see. I don't even know what this is telling me. I'm not sure, honestly, if it gives partial or not. Even looking at this this is like the most useless breakdown I've ever seen. Let me see.
Yeah, for the first one, I got one of them right, or for one of the answers that you said were correct. But on another question, it gave me partial credit.
I see.
So I don't know if it was just the first question that did that, or.
I'm not sure how it's plugged in. I'd have to go. I'm trying to go in and look at it right now, and I can't figure out how to work the interface for Canvas. But like, it's possible that one had partial credit and one didn't. Did you select one correct and one wrong, or something like cancel them out? Actually, let me see if I can just look in. I'm sorry, who's speaking? Is it Avery? Is that?
Yes, Avery.
I can just go and look at your specific exam. Maybe that's the way to do it. Okay, I think I'm there. Yeah, okay. It looks like I can't see your exam because the UI here is just taking a million years to do anything on. But it looks like it gives you half credit. So if you got one correct versus the other, oh my God. So Canvas is Canvas is not that this really matters to you guys, but Canvas is really well designed if you have a class of like 20 students. For 200 students, it's just like I can't quickly sort through the stack. Let me see. I might be able to get there. So I can at least tell you what went wrong since we've been on this. Just click a few million more times here. There we go. Okay, yeah. So what happened was you answered correctly on one of them, but then you checked one of the ones that was also incorrect, so they just cancel each other out. So if you got one of them correct, so if you'd have just clicked, for example, one of the correct answers and not clicked anything else, then you'd have gotten half credit for it. But since you clicked one of the correct answers and one that was incorrect, then it just subtracted 2.5 points for the incorrect one. Does that make sense?
Okay, yeah, I got it.
Yeah.
And then what were the answers for number 18, just so whenever I review, I know.
Sure. Does it not tell you the correct answers at the end? I guess we probably have it set not to do that. Number 18, it's copper. Number 18 is, oh yeah. This is the one we went over. A saturated solution, yeah. This one is, so the solubility will decrease for that, and then you'll also see some precipitation. This is really a common ion effect. Both of these things come from common ion effect. It shifts the equilibrium to the left. If you're trying to look at where the answer for that lies.
Okay, thank you.
Yep.
Were you able to on Monday you said it sounded like you were going to give credit back for number 21 if you chose and it shows a negative of the correct answer, you sounded like,
Yeah.
correct me if I'm wrong, but you sounded like you
No.
were doing that in real time. But
Yeah, that should have fixed it. Let me go and check. Did it not go through?
I asked people, no one said anything, but maybe I just got the wrong answer
So it's,
regardless.
there were two possible answers. I forget exactly how that shook out. Let me take a look at it real quick. Question 18.
I got negative 0.0063.
Oh, right. Yeah.
But is that the positive that or the correct answer?
Right. Oh, right. The last one, question 21. Yeah, did it only fix it for one person? Hold on.
Yeah, I got the same answer and it's still counted wrong.
Okay, let me go and try again and see if it fixed it. Maybe it just updated it. I don't know why that didn't update. Okay, it's going in. Both corrected. Award points for both corrected and previous correct answers. And scores will be reduced. That is what I want. All right, now let me go in and check and see if it fixed it. If I can. Yeah, maybe I forgot to hit save or something. I don't know. Let's see what happened. So. Oh my gosh, so slow. Yeah, sometimes it takes a little while to go through, but not multiple days. Let's see. This is such a cluster. There we go, exam 3. It doesn't look like it changed. Okay, all right. I think it fixed. I think it fixed.
Yes, it fixed. It
Okay.
fixed. I see.
Yeah, it just took a few seconds to go through. All right, we're good. All right. Yep. Sorry about that.
Thank you very much. Thank you very much.
Yeah, I'm pretty sure the negative one is the correct answer on that one. So you definitely should not lose points for not putting the negative sign. If anything, the positive one should be taken away, but that's not how we roll. Okay, but yeah, the averages on this exam was pretty good, so that makes me happy. The first exam was kind of rough. Any other questions? Have you guys started with the electrochemistry stuff yet? If you had a good high school instructor, my high school My high school instructor was solid, but we just didn't go through a whole lot of stuff. But we did luckily go through redox equations, so I wasn't taught off guard with that. But it does take a little while to get on them. The rest of the stuff is pretty standard. I don't think it's any harder or easier than anything else we've done. Easier than acid base, but no harder than kinetics. And we haven't really got there yet, so. Yeah, just try to at least get through try to start playing around with the redox stuff. That's obviously it's always a good idea to get started early on studying, but if you have time, at least try to get started balancing redox equations. The rest of this stuff, I never recommend cramming, but it's more crammable than the redox stuff. That's just a lot of anxiety, I think, going into the exam, not being able to do that the week of, for example. I know I feel like it's like exam after exam after exam, but we're almost done with the semester, so that I guess is at least good news. And we'll have a little bit of a break over Thanksgiving. Do you guys have any other questions? The finals the week after the last exam. It should hopefully at least be on the Canvas page. Let me go look.
It's on the 12th of December, so a little over a week after.
Yeah, December 12th. Yeah, I'll look at what the rules are for like how we can deal with the final and stuff and what we end up doing with it exactly. But right now, just expect it to be on the 12th. Yeah, just expect it to be on the 12th. The university's they're like semi-strict about what we're allowed to do this semester. I think just because they know that they don't want to piss the students off any more than they're already pissed off because they're taking classes online and they're paying full tuition. So we'll see. We'll see how that shakes out for the final exam. If we have to give it the exact day or what it can be, if there's some flexibility, or if I have to give final at all or any of that kind of stuff, I need to check with the department to make sure I'm above board. So just assume the syllabus is our worst case scenario. Anything else?
Thank you. Have a nice day.
Yeah, you guys have a nice day too.
I had a quick
go
question
ahead.
about balancing the redox reactions. So in the LE, I saw that they would add coefficients before doing like any of the balancing and all of that with adding H2O and H plus and all of that. How do you know when you need to add a coefficient to the reaction before doing any of that, if that makes sense?
Yeah, it does. So for example, let me see if I can find one real quick that has that in it. Let's take a look at this one. It's basically, the short answer is just that you always want to balance the coefficients out first, but only for things that are not oxygen or hydrogen. So if we split this reaction into its oxidation and reduction half cells or half reactions or whatever, we end up with chromium +2 going to chromium 3. So this is our oxidation reaction. And then we have this sulfur compound, S4O6 -2 going to S2O3 -2. What you're looking at is you're trying to balance anything that's not oxygen or hydrogen. So the first one is easy. There's no oxygen or hydrogen. So we're just making sure that the number of chromium atoms on the left hand and the right hand equal one another. And these both have a implied subscript of 1, so we're good. We don't have to do anything to that one. But if we come down here to this one, we see that we have 4 sulfurs on this side and only 2 on the right side. So your first step is just to balance that. So you're balancing anything that's not oxygen. So we added 2 there, and that's it. So it's only the time that you add a coefficient is only to balance out things that are not oxygen or hydrogen. So I put a 2 here, and the other one I think we had like manganese. Does that make sense?
Yes, it does. Thank you.
Yeah. So I think the other one we had was like manganese. I gotta go back and look. Or like here, like, so this is a good one. So here we have aluminum. I've already balanced it with the 2, but here I had aluminum going to aluminum oxide. And so I don't worry about the oxygens or whatever, but I do need to balance those aluminums out. So I need to take that 2 and I put it in front of the aluminum over here and get that balanced. And then the rest of the stuff I don't worry about. That ends up sorting itself out here. But yeah, that's your first step. So break into half reactions, balance all the elements that are not hydrogen or oxygen. That means add a coefficient. And usually it's a 2 or something. A lot of times you don't even have to do that. So yep. This is, I think, for redox, aside from, it's just a matter of practicing going through the steps like 5 or 6 times, and then you kind of get it. Don't do it when you're tired, because then you get a bunch of weird carryover mistakes and get really frustrated. All right, I will see you guys on class on Friday, and then Monday, and then Thanksgiving, and then Monday. So I'll see you guys soon, and we'll get started on this other stuff, the galvanic cells.